Hello everyone, this is experiment 12. We will be doing reflection, refraction, and the dispersion of light. If you have access to your physical lab manual, you will also see Brewster's angle listed. For brevity's sake, we are not covering Brewster's angle. So the materials online have had Brewster's angle removed, but if you see it in your lab manual, don't worry about it. We are not covering Brewster's angle. So, just kind of jumping right off into it. This is, as far as lab goes, pretty simple conceptually. We're just looking at three different laws, two different laws, and then some interesting features of the second law that we'll be covering. So this is should be pretty straightforward. So first off, in section A, we're covering the law of reflection. No fancy names, just the law of reflection. And this simply states that the angle of incident of is equal to the reflected angle for a single ray of light, right? So if we look at this diagram, we've got the reflecting surface here, we've got the incident ray coming in, and then we've got the reflected ray coming out. The important thing to note is both for this law and the second law we'll be covering, the angle is in reference to the normal line of the surface. So part A is going over different, we use two different curved mirrors. So this law doesn't change depending on the shape of the surface. What matters is at whatever point on the surface the light ray impacts, you draw a line that is normal, so 90 degrees to that surface. And from that normal line onto the ray is the angle that the law of reflection is referring to. So part B is Snell's Law, named after a person with the last name Snell. It looks similar to the law of reflection, but because we're covering refraction, Snell's law refers to refraction. It's a little more complicated. And so we introduce this quantity n, which is known as the index of refraction. I think there's a couple other names for it, but that's what we're calling. We're calling the index of refraction. And so this is concerned with what happens when we have a transition between two different substances, right? So we have an incident ray coming in. It hits this transition boundary between two different substances. The picture in your book, which I've kind of recreated here, says, okay, what if we're transitioning from air to glass, right? What we see is it bends downward, right? So, and then we've got this refracted ray coming through the second material. So again, we have the same setup where the angle is concerned with is in relative to the normal line. So what we have here is the index of refraction of material 1 times the sine of the angle of incident is equal to the index of refraction of material 2 times the sine of the angle of the refracted ray, again in reference to the normal line. So just to recreate something that I've got listed over a little on the left, the index of refraction is defined as the ratio between the speed of light in a vacuum and the velocity of light through whatever material we're concerned with. So the index of refraction of vacuum, I don't remember how to spell that. Alright, so vacuum, let's just leave it as vac, is strictly equal to 1, right? Because the speed of light in a vacuum is c, so c divided by c is 1. For our purposes, we will consider the index of refraction of air to also be equal to 1. It's not exactly equal to 1, but it's very, very close, and so we're making this approximation that I guess I should formally, right? The index of refraction of air is approximately equal to 1. And again, we've gathered some data showing this, so you'll do some calculations with the data we gathered, and you'll be able to verify that this law is true. Finally, for part C, which is the final part that we'll be covering, is on a topic called dispersion, which is very much related to refraction, right? So if you look at the setup here, the picture of the setup, we have a light ray coming in, it's refracting into the material, in this case an acrylic prism, and then it comes out the other side back into air and refracts once again. And what dispersion is concerned with is it's recognizing the fact that the index of refraction is wavelength dependent, right? So different colors of light interact with different materials slightly differently, or slightly more strongly or weakly, right? And so what the setup for this is, right, the light comes in, it refracts through the material, and then it refracts out. And so what you would do is you would measure this angle inside the material, which would be your incident angle as it comes out the other side. And then this is not to scale. In practice, it would be a good ways out, probably, I don't know, out to here-ish, before you would see a very slight separation of the red and blue light from the white light source. So in our case, it's a very small effect, so this drawing here is exaggerated. It's also, I don't know why I did two, oh no, that's an E. Sorry, it's also important to mention or point out that there's nothing magical about this transition. Light is dispersing from this first transition through the material. However, because the effect is so small and the distance is so short through this prism, you would not be able to see that with the setup that we have. I apologize for my phone. You would not be able to see the dispersion through the material with the setup we have. So it's, again, we would only see it much further out here on the paper if you were to draw it physically. So this is a slightly exaggerated view, but as soon as you hit as soon as you have this refraction, there is dispersion occurring. We just can't see it. And yeah, that pretty much covers the basic theory on what you need to know to complete the lab.